Hello. Hello, thank you to the organizers. I am Gonzalo Barajas. I will be presenting this work. I come from EPCIT in San Luis Potosí, Mexico. The work is titled Hidden Attractors of Jerk Equation-Based Dynamical Systems. It's a work by student Daniel Ponce Pacheco and myself. Thank you for coming. The outline is a small introduction. We're going to discuss the analytical numerical localization method proposed by Lenov and his application to the jerk dynamical systems that we will be discussing. A very simple introduction would be that dynamical systems in general can be identified as an equation, a simple dynamic differential equation. And then for these solutions of this differential equation, an invariant SAT would be given an initial condition, the application of the dynamical system description will have the solution remain in the same set. Then from this definition, we can understand an attractor as a small neighborhood around this invariant set that becomes that converges towards this invariant set K. Therefore, you can call the region of the steady space where these invariant sets is attractive as a spacing of attraction. With these basic concepts, we can describe attractors into two types. Self-excited attractors, which is the name that we give to attractors that intersect their basis of attraction, intersects a neighborhood of an unstable equilibrium point, and hidden attractors, which are have the characteristic that they don't intersect the neighborhood of an unstable equilibrium point with their basis of attraction. Self-excited attractors are very simple to identify since you start near an equilibrium point, and if this attractor exists, then you easily converge to it. Hidden attractors have been more recently of interest because they appear in places where we would not expect dynamics to exist. By definition, this type of hidden attractors can be found in systems without equilibrium points, systems with only stable equilibrium points, and systems with an infinity of equilibrium points. Finally, the most common version of hidden attractors are the ones that coexist with self-excited attractors. In particular, we're going to be working with the jerk equation, which is a third-dimensional linear dynamical equation that represents position, acceleration, position, velocity, acceleration, and jerk. Jerk is equal to a nonlinear function in particular. In this case, we're going to consider that that nonlinear function is piecewise linear. Therefore, we have a piecewise linear system generated by the jerk equation. For example, if we say that the nonlinear function has two components, then we can define a system like this one. And in particular, we use the piecewise linear function that is discontinuous. It jumps from minus 0 minus 0.8 to 0.8. So that's the discontinuity. And it generates an attractor like the one in the figure, and it has a self-excited characteristic. It's generated and is close to the vicinity of unstable equilibrium points in this case. Then the analytical numerical method proposed by Lenov to identify hidden attractors starts with the idea of rewriting the original system as a Lure system, where you have a linear part plus a static nonlinear component that can be seen as the nonlinearity in the input. Right? With this one, you can do harmonic feedback linearization, which basically means to force the linear part to have only two types of eigenvalues, purely imaginary or negative real part eigenvalues. From that, you can construct a perturbed version of the original system with harmonic feedback linearization. Basically means to have a linear part and adding the static nonlinearity, you can say little by little. So you have epsilon zero, which is very, very small, and then you do a very basic stability analysis of the linear perturbed system to try to identify if a stable oscillation is possible. And if a stable oscillation is possible, you keep that as the initial proposal for the hidden attractor. This is gamma, capital gamma sub zero. Then you do a numerical investigation. The numerical investigation basically starts with this proposal for a hidden attractor, and then you start incrementing the perturbation until you reach one. This incrementation, or as you increment the perturbation, numerically you try to identify the location of the oscillations, and if the oscillations do not become unstable or disappear, then when you arrive at perturbation equal to one, you can say that this is an attractor of the original system. Then you have to verify if there are possible variants. In the case of a symmetric system, possibly the other side has also a hidden attractor. And another way you can find variants would be to look for different natural frequencies of the originally perturbed system, the epsilon zero, and try to see if another values of omega can satisfy the conditions for stability. And finally, you need to determine whether this attractor is self-excited or not. This is very simple. You start near an equilibrium point, and if the trajectory converges towards your found hidden attractor, then it is not hidden, right? Self-excited. Finally, we did this analytical numerical investigation for our version of jerk systems. And you can see the construction is simple. We only use static nonlinear functions that are piecewise linear only on x1. And we identified that for the equilibrium points to have different types of stability, you would need to have alpha, beta, and gamma solving this characteristic equation, whatever is necessary. From that, you can find the perturbed system, and it's very relatively simple to identify the values of the feedback to have harmonic feedback linearization and the frequency where you are oscillating in the linear perturbed system. From that, we do the numerical investigation, in particular for this type of nonlinearity, which is similar to the previous one when you have a discontinuous two-part piecewise linear function. And then we go with these parameters and move from our candidate hidden attractor towards the original system. And we find an attractor. The only problem is the same attractor as before, so it is a self-excited attractor. So we couldn't find for this type of systems, even if we change the parameters, a hidden attractor. We have attractors, but they are always self-excited. Finally, we found a version of the three-part jerk system where the nonlinearity is like that. This nonlinearity is continuous in the sense that there's no gaps, but is non-differential for 1 and -1. So it's a piecewise linear, similar to the Chua nonlinearity. For these parameters, we found a hidden attractor. And obviously, since it's a symmetric system, we investigated also for the negative version, and it has, in this case, two hidden attractors. We looked for the self-excited attractor, and it's the one in green. So we could find for this particular system two hidden attractors and one self-excited attractor. So they are coexisting. In the closing remarks, I would like to say that basically in this contribution, we applied the analytic numerical methodology proposed by Lenov for a particular very simple system, which is the piecewise linear jerk system with 2 and 3 components. We did different types of different values for the parameters. We did a very extensive numerical analysis. And for n equal to 2 and a discontinuous piecewise linear component, we couldn't find any hidden attractors, only self-excited attractors. And for n equal to 3, we found two hidden attractors in the example that I just gave you. The final comment is that the key factors are the parameters. We need to determine the stability of the equilibrium points or the description of the piecewise linear function. Further analysis and generalization of these findings is underway. We believe that it's very significant that discontinuous piecewise linear functions do not necessarily have a hidden attractor in the vicinity of the equilibrium points, and that three parts continuous it does, right? So probably there's a connection there. Well, that is the end of my presentation. Thank you for your time and attention. Any questions, please, you have here my contact information. That is my email and my telephone number in Mexico. And well, I hope to hear from you. Thank you very much to the organizers again. And that's it.